So what we wanted to do last time was to prove the positive side of the fundamental theorem. So we want to prove that basically the positive direction of the fundamental theorem and that was that for every class H, for every class H, we have that M H, say uniform convergence, is upper bounded by some constant. So this is for some fixed C. This is upper bound by some constant times the VC dimension of H plus log 1 over delta divided by epsilon square. And we had a similar result for the PAC, exactly the same result for the number of examples. Oh, come on. M uniform convergence with respect to H of epsilon delta. Right? And we had a similar result for the rate of, exactly the same result for the sample size needed for agnostic PAC learning. So the same thing with agnostic PAC learning. And with PAC learning, we got even a slightly better result where we had dependence over with epsilon in the denominator rather than epsilon square in the denominator. So the main thing we want to show is that I can control the learning rate. I can control the number of examples that I need to learn as a function of the VC dimension. Now, so what I want to start with is the kind of the proof sketch. So the first step, I mean, we can start imitating. We've already seen such a result. We've seen such a result, which was not in terms of the VC dimension, but instead we had here the log of the size of H. So we can start imitating that proof and see where we need to deviate when we want to prove it with respect to the VC dimension rather than the log the size of H. Right? So just note, this is a stronger result. So just let's put it here. Just recall, we have already seen that for any finite H, we get exactly the same result and with one small change, is at most some constant. And here I had log the size of H plus log 1 over delta divided by epsilon square. So we already had this result. That was the result that finite classes are learnable. So first of all, note that the VC dimension we know is always at most log the size of H. So this is always an improvement. The VC dimension is always at most log the size of H. So we save samples. We are not losing anything by moving to this bound. But the big advantage of moving to this bound is it allows us to also handle infinite classes. So many of the classes that we have already discussed and saw that they have finite VC dimension, like this class of all singletons, of all spike functions, or the class of all half spaces, or this class of all rectangles. All of them are infinite classes, so this result does not hold for them. but they have finite VC dimensions, so they will be captured by this result. So this gives us a much wider scope of H's that we can cover. But since the result is so similar, we can start the proof by trying to imitate the proof that we had here. And then we'll see where we get stuck and how we can try to overcome it. So how did the proof of this result go? So the first step was just using a result from probability theory, the Hoeffding lemma. We saw that for every fixed H and every epsilon and m and every probability distribution P over x cross 0, 1, we know that if we look at the probability, when we take a sample S according to P to the m, so the sample is generated by taking m times independently at random a point and label generated by P, the probability that Ls of H minus Lp of H will be greater than epsilon was less than 2e to the minus 2m epsilon squared. So this was a basic result that basically was just probability, because this is just the average of a sample. This is the expectation. This is the expectation that the loss with respect to P is defined by the expected loss when we draw a point at random. And Ls is defined as the empirical loss when we drew m points and we take the average loss. So this is the average over m points, and this is the expectation over the distribution. And this is a general result that if I take any random variable and try to estimate it with epsilon, with m many independent trials, then the average that I calculate converges to the true expectation. Right? If I have a coin and I'm trying to estimate the bias of the coin, so I can toss the coin m times, look at the average of how often does it fall heads, and we know that this converges to the true bias of the coin. That's what we have here. Just the average over m tosses of the coin, and this is the true bias of the coin, and this converges exponentially fast. This minus means that the number that I have here, right, it looks like 2 over e to the m epsilon square, so it goes down exponentially fast with the sample size. Now, why didn't this suffice? Because this result is only for an H that I fixed before I saw the sample. I pick my coin first, then I toss it and sample it. So this holds if I pick H before I see the sample. But what we want to do in learning is get a sample and based on the sample to figure out which is our best H. So in order to allow this, we need something stronger. We need uniform convergence over all H's. So we need something stronger. So the second step we are still following the proof of the case of finite H. The second step was saying if we wanted to hold for all H's, we should use the union bound. So we say that the probability and what we really care about, so again, we sample S according to P to the M, but we ask, could there be even one H in which the bad case happens? we want to make sure that no h in H will fail us, not that a particular one that was picked in advance. So the probability there exists an h in H such that we have this kind of failure, Ls of H minus L P of H is greater than epsilon, we want to bound this probability. Because we have many h's, and in order to be able to pick an h after we saw the sample, we want to guarantee that none of them is going to be misevaluated. So this is the addition here. And for this, we use the union bound. We know this is by the union bound because the probability there exists such an h is the union of all the probabilities over the different h's. So this is by the union bound. I just have to count how many h's I have. I have h many h's. And now I can repeat what I had before, times 2e to the minus 2m epsilon squared. So basically the argument here was that if I fix an h, then the probability that I'll get a sample that misestimates the error of h is very small. But if I have many h's in my class, so maybe these are the samples that will make h1 misestimate h1, and these are the samples that will misestimate h2, and these are the samples that will misestimate h3. And if I want to make sure that none of the h's will be misestimated, I need to multiply this area by the number of h's that I have. So that was the proof for the finite h. Now, the main point was if h was finite, this is a fixed number. As the sample size grows to infinity, what will happen to this probability of failure? It goes to 0. It will go to 0. Because this goes to 0, as m goes to infinity, this stays fixed. So the probability of failure will go to 0. So in other words, if I want to pick some delta and make sure that this happens with probability delta, a big enough n will suffice. And how big is big enough is completely independent of the probability p. And that's exactly the learnability result for finite h. So what goes wrong if h is infinite? Yes.
Multiplying the cardinality of h by the...
Yeah, multiplying by the cardinality of h. If I have infinitely many candidates here, it could be that in total, the probability of failure is very big. OK, so we have to somehow replace this infinite h by something that is more controllable. So now I come to the first attempt that I already mentioned at the end of the last talk. So the first attempt is saying, what are we actually doing here? We're going to apply ERM. We are going to apply, we wish to evaluate the success of ERMH. What does ERMH do? When it sees a sample, I pick an h that behaves best on the sample. So I have my sample, and I'm picking an h among those that behave best on the sample. But all I can see, all I care about, is how h behaves on the sample. So we only care about the behavior of h's on the sample S. Because our algorithm only looks at how many errors you make on the sample. The algorithm doesn't care what my function does outside the sample. But on the sample, I know that I have only few behaviors. So, however, on S, the set of all H intersection S, or the behaviors on S, such that H is in H, this is a finite set. And furthermore, by the Sauer lemma, by Sauer, it is bounded by M to the VC dimension of H. So the set of functions that I want to make sure that they don't misestimate the true arrow is not an infinite set, because all I care about is functions on S that are just the restriction of a function on all of x to S, right? And those I have at most M to the VC dimension. So maybe I can just put here M to the VC dimension. And what will I get if I use it in the bound here? I'll get M to the D times E to the minus 2m epsilon square. What happens to this bound? Because M to the D will be the bound on the number of behaviors of H on the sample, which is all I care about. What will happen to this quantity when M goes to infinity? So let me rewrite it so we will be able to see what happens to it. We get here M to the D times 2 divided by E to the minus 2m epsilon square. So what happens to this guy when M goes to infinity? Which of the two grows faster? Yes. The exponential will grow faster than the polynomial. So as M goes to infinity, this will go to 0. And that's what we want. Now, if you followed what I was doing, you should now feel maybe we finished the proof. We showed that if I want to decrease the probability of failure, if I want to decrease my delta for every epsilon, and I want to make my delta small enough, I'll pick M big enough. That will be my MH of epsilon delta, because big enough M will make this delta arbitrarily small. So it looks like the theorem is proven, but we know that it's not because I called it a first attempt. So what is wrong with this line of argument? Yes?
You're bounding the probability for a class of functions, but within that class, you still have infinite.
Yeah, I cannot. You say you are bounding the probability of a class of functions. That's what I want. I'm bounding the probability of failure on a class of functions. The class have infinitely many functions. But what I'm saying is that what I care about is just this behavior of an H on S. So although the trick is that, so here is my X. Here is my X. And say this is my sample S. Now I have infinitely many functions, but many of them behave the same on S. And all I care here is finding the function that behaves best on S. So if I find a function that behaves nicely on S, if I just say this will hold for all behaviors on S. So I'll see a behavior on S, and I'll say, for an H that behaves like this, I know that the true arrow cannot be too big. And every H in my infinite class will pick one of those few behaviors on the sample S. Because by the Sauer lemma, there are only few behaviors on the sample S, although H is infinite. Yes?
two h's that agree on s but disagree on their s, then the probability of getting either one of them would be bounded by the sum of the probabilities. So you can't just treat them as the same one. Treat them as the same one because the probability of getting one or the other is bigger than the probability of getting just the one.
You see, on one hand, I want to repeat answers for the recording. On the other hand, I don't want to repeat answers which are not. So maybe you have a point. I'm not sure. But OK, so let me tell you what is the secret here. The secret here is in the order that we do things. Here, I first choose the sample S. And then, based on S, I defined what are the functions that I care about. And that's kind of illegitimate. What we know is that if I have a set of functions that I care about, and now I'll take a sample, then it will estimate all of them nicely. But here I reverse the order. The set of functions that I care about is the set of behaviors on S. I know which functions it is only after I see S. So the order is reversed. Right? I cannot, if I want to estimate the behavior of a coin, right? I know that it will give me a good estimate if how do I say? Yeah, if I first have to pick my hypothesis, and then I draw a sample and I test my hypothesis. If I design my hypothesis based on the sample, then this argument no longer holds. And here I design my class of functions based on S. And S was my sample. Yes?
So this is not for any S then, this inequality?
Which inequality?
The Sauer lemma.
The Sauer lemma holds for any S.
So I don't see how you design your hypothesis class based on S.
Oh, what I was saying is that I can replace H. In order to go from infinite to m to the d, I said we could replace H by just the set of behaviors on this specific S. This depends on S. No, the size will be OK. The size will not be the problem. The inequality just tells me that the size of the... what I did is I looked at a set of functions that I can call HS, all the behaviors on S. The size of HS by the Sauer lemma is bounded. But HS, the choice of HS, was made after I saw S. So now I cannot use S as a fresh, naive sample to estimate functions in this class. If I chose this class after I saw S.
So I'm not allowed to say for any S, choose some, or so for any S, HS, or this.
Let me maybe try to demonstrate what the problem is. Right? So assume that I'm trying to estimate. Here I have some probability distribution. Say my probability distribution, I mean, it picks the points x. So here is my x, and my probability distribution picks points and picks labels either 0 or 1. And assume that I just have two functions that I want to estimate. What is going to be the error of the function, which is always predicts 1? And what is going to be the error of the function that always predicts 0? Right? So what do we know? We know that if I just pick a sample S here, I can see how many times I got 1, how often did I get 0, and I estimate simultaneously both of them correctly. If S is big enough, the fraction of 1s will give me roughly the error of the function 1. The function of 0s will give me roughly the error of the function 0. Okay? But here I chose the two functions before I saw the sample. Now let us assume that I'm doing it the opposite way. I first see the sample. So I see the sample, and the sample tells me, on this point, I got 0. On this point, I got 1. On this point, I got 1. On this point, I got 0. On this point, I got 1. That was my sample. Now I will choose my function. I will ask, what is the error of this function? Now, according to the sample, what is the error of this function? 0. Do you think it really has 0 error? No. What went wrong? I chose my function based on the sample. That's the problem. And that's what we are doing here, because we chose the set of functions that we are going to estimate to take the union over based on the sample. And that's an illegal move. Okay, does it make sense now? So that was the subtle catch that we have to overcome. We are not allowed to use the class based on the sample. But we do know that Sauer lemma helps. And so how do we make it? How do we make it work legally? Okay, so what we are going to use is something which is called the double sample trick. So this is called the double sample trick or argument. And the double sample argument goes in 2 steps. Step A says the following. I will choose, I may evaluate the arrow of any function in HS in the class of behaviors on S by using a fresh independent of S sample T. So what I'm going to do is I'll first take S and look at all the behaviors that I have on S. And then I will not estimate the arrow based on my arrow on S, but I'll draw a fresh sample T, and I'll estimate them according to the behavior on this fresh sample T. So the claim here is that the probability that we want to estimate, the probability, this is what we really want to estimate, the probability over S sampled according to P to the M, that there exists some H in H such that LS of H minus LP of H is greater than epsilon. That's what we want to estimate. Is bounded by 2 times the probability, and now I will take S according to P to the M and a fresh T according to P to the M independently. So I take a double sample. The probability that there exists an H in H such that LS of H minus LT of H is greater than epsilon. So the probability that I look at LS of H and I ask how well is it estimating the true error of H. What I'm saying is to evaluate how well I'm estimating the true error, I'll draw a fresh sample T and I'll check how much error I make on T. Since T is independent on S, this is kind of a reliable evaluation process, validation process. Yes. What do you say? Oh, I didn't prove it. I'm just saying when you try to prove it, you lose a factor of 2. But because instead of telling you exactly what's the error of h on the true distribution, I'm just testing it on this fresh sample t. So I may have some kind of bigger error. And what I'm claiming is that I want you to intuitively understand why this argument makes sense. I want to evaluate my error on p. I'll just draw a fresh sample t and evaluate my behavior on t. And it will be a kind of, I'm looking for the word, something like reliable, what? Sound, representative way of evaluating how well the probability does. Because it's a fresh sample, it's independent.
Does this also not change with m?
What?
Does this also not change with m?
Oh, no, I want to bound this probability. Of course, the bigger the sample m, the smaller this probability will be. But we fix an m. For every m, we'll have this factor of 2. So that's the basic idea. Now, why did it save me? Why is it easier for me to bound this difference than it was to bound this difference? Because now, what I can do, so now we want to bound this guy. To bound this guy, we show that, no, we know it doesn't work, right? Okay, I'll hold it. For every pick any subset A of X of size 2m, and now we will bound the same probability, this probability. So we will bound, I don't know if it's better to give it a name or to just rewrite it. So let's give it a name. So let's call this event is the bad event with respect to S and T. And this is a bad event with respect to S. A bad event with respect to S, it means that there is a function in my class that S misestimates. A bad event with respect to ST, there is a function in my class that the estimate according to S differs from the estimate according to T. So I want to bound the probability of the bad event, probability of over S and T according to P to the M of the bad event ST given that S and T are subsets of A. So I fix some set A, and I will bound this probability given that the samples came from A. If I can do it for every A, then we are done. You see, because here is my X. I pick a sample S, and I pick a sample T. So this is some set A. No matter how I'll pick S and T, it'll be some such set A. Right? So the total distribution over S and T is just a union over all these A's. If I show that all those A's have small probability of error, then there's a small probability of error over the whole set. Okay? So this is a very basic kind of type of argument in probability theory. If I want to show you that the probability that a student will fail this course is at most 10%, then I can divide this course into two types of students, those that have glasses and those that don't have glasses. If I show you that for those that have glasses, the probability of failure is at most 10%, and for those that don't have glasses, the probability of failure is also at most 10%, then since every student either has glasses or not, you know that the probability that a student will fail is at most 10%. So I divided my space according to the sets A, and given any such A, I'll show that the probability is small, then we'll have that the total probability is small. What did I gain by dividing it by such an A? Because now if I fix A, all I care about is the behaviors of H on A. You see, all I care about is the behavior of H, how H behaves on S, how H behaves on T. But the union, the set A, I pick it before I see the sample S and T. I pick a set A. I say all I care about is the behaviors in this set A. Then I pick an S and T inside A and evaluate how different they are going to be. So now I'm using the fact that, but for that purpose, for this evaluation, it suffices to consider H restricted to A. Just the set of possible behaviors of H on A. Because I first pick A, I see how many behaviors I have, and then I pick a sample S and I pick a sample T, conditioned they are in A. And so now what we get is that we get that the probability of failure, the probability of the bad case ST over ST P to the M, coming from P to the M, is at most, now I am asking, if I pick a set S A of size 2M, how many behaviors do I have? I have at most 2 to the M to the D behaviors. This is how many behaviors I have on A. Where is this coming from? Sauer's lemma. And now I have 2e to the minus 2m epsilon square. And this thing goes to 0 as m goes to infinity. And the probability of the bad event with respect to S is at most twice the probability of the bad events with respect to ST. This is for a sample S of size m. And here I pick S and T, each of size m. So I got a bound on the probability of failure that goes to 0 as m goes to infinity. So with the double sample trick, I managed to get rid of this connection between the sample S and the set of functions that is relevant. If I pick this big A, I first pick this big A, look only at the functions, how they behave on A, and now inside A, I pick S, I pick T, but the set of functions was already fixed before I randomly drew S and T in this set A. So that's a double sample trick, and that's how the VC dimension and the Sauer lemma give us learnability of classes of finite VC dimension. The main point here, what would have happened if I didn't have the Sauer lemma? If I didn't have the Sauer lemma, then how many behaviors could I have had on a set A? Yes?
2 to the size of A.
2 to the size of A. So without the Sauer lemma, I will get that this probability is bounded by 2 to the size of A, which is 2 to the 2m, times 2e to the minus m epsilon square, and so on. But you see what is happening here. Here I have a positive exponent in the denominator, exponent in the denominator, and it's not going to 0. This whole thing, what I would have got here is 2 to the 2m divided, another 2 divided by e to the minus m epsilon square. What? Without the minus, right? So I will get something like 2, and here I'll have 2 to the 2. It's 4 over e something to the power m epsilon square. But this is not going to 0 when m goes to infinity, because this guy is bigger than 1. And it's not going to 0. It's going to 0 only because of this wonderful phenomena of the Sauer lemma, that instead of exponential number of behaviors, I have only polynomial number of behaviors. Yes?
So from our claim, I see how we turned the term on the right into this expression using the Sauer lemma. But when did we show that it actually is greater than or equal to the probability on the left-hand side?
When did we show? You are wondering about this?
Yeah, like when did we establish, like we claimed
No,
this relation?
I'm saying this I did not prove.
Okay.
I didn't prove it. This was the part that I didn't prove. It's not very difficult, but it's kind of not. It's just saying that if you want to estimate something with respect to a probability, take a fresh sample, estimate with respect to the fresh sample, you're not losing much. And I didn't prove it.
Okay.
So that the fact that you don't know how this is good. I mean, it's a sign that you did not hear anything just from inside your head. Yeah. Okay. So you see, that's how we use the Sauer lemma, to replace this potentially exponential number of behaviors to a polynomial number of behaviors. Okay, so we are done with this proof. That's basically the idea, how Sauer lemma gives us the ability to replace an infinite h with just its VC dimension. But of course, I mean, yes.
So it occurs to me, so why do we choose an A that's of size 2m when it's because S and T are independently chosen, right? So they could overlap. They're not going.
But if they overlap, then it's no more longer independent. If they overlap, there's some delicate problems there. But the point is that if they overlap, then the estimate according to S and the estimate according to D are no longer to T are no longer independent.
So S and T are chosen.
The S and T should be. I mean, I'm kind of choosing. I take a set of size 2A, and I randomly choose for each point if it's going to go to S or to go to T.
Okay.
Because I want that the estimate according to S and the estimate according to T will be independent.
Okay.
Yeah, it's a good point. Anyway, I mean, we all know that if a professor stands in front of you and gives you a long proof, it could, at the end, you will admit that you are convinced, regardless of what he was trying to prove. So if you really care about understanding it, go to the book and read the details and think about it and come back and ask me questions. Because the proof is long enough that, I mean, you should be suspicious. I had enough opportunities to try to cheat or to collect small cheats into a big one. But I'm just trying to give the basic idea. I don't think that we should go into more details in the class. If you really care about it, we have taken care to give details in the book. Okay, where are we now? So now we have established that a class, so the big conclusion is that a class H is learnable if and only if it has finite VC dimension. How good is this? I mean, what does it give us when we want to, in practice, do learning? So as we said, I mean, if you want to learn something, it is very important to choose a right age. If I'm trying to learn if a papaya is tasty or not, and I chose the wrong age, I chose to evaluate it by the color and the softness, but it's the wrong age, then I mean I'm going to fail. I can give you. I wonder if I can give you a simple example. I mean, of course, the papaya can fail because I chose the irrelevant features. But even when I have relevant features, the no-free lunch theorem shows us that if we wanted to evaluate all the functions according to those features, it will be impossible to learn. We need to make a commitment to a smaller set. And how much is it of a limitation? I mean, how much do we have to know about the problem? So if you get a problem, the procedure is like this. You get a problem that you want to solve. You want to learn something. Which papayas are tasty, which emails are spam, which patients are at risk. It doesn't matter. You get a problem. What we propose is that you will go and pick some hypothesis class, H, of finite VC dimension, and then learn pick S, and learn with respect to H. And what kind of guarantee can I give you? I can give you a guarantee that your hypothesis will be close to the best in H. But maybe you picked a bad H, and close to the best in H is not good enough. You see what the problem is? When we pick H, we are limited. H cannot be all possible functions. It has to be a very restricted family. It could be infinite, but it still needs a finite VC dimension. So maybe the guarantee that I get is that now the H, the little h, the hypothesis that I learned, is as close to be as good as the best in capital H. But it seems like we have to know a lot about our problem to start working with it. So I want to make, I mean, the question is how much progress did we make? So I want to make two arguments about it. So maybe, what I'm telling you is that if you knew enough about your problem to pick a good H, maybe you already knew enough about your problem to pick a good hypothesis. How much progress did we make? So there are two arguments that can show us that we really made progress. I mean, we know that one argument, kind of external argument, is saying we know that machine learning is very successful. We know that Google pays to fresh out-of-school students $250,000 a year. It must be working. But more to the point, I'll give you let's see two arguments why it works. So first of all, how useful is, or how relevant is such a paradigm? So the first argument, argument one, sometimes a fixed small VC H is all we really care about. So, for example, an example of this situation, say I want to have to recommend how many calories should a person eat per day. Right? So I can take a sample of people and check for each of them how many calories they usually eat per day, and then classify them into healthy, not healthy. And then I'm trying, based on this, to give you recommendations about what is the right number of calories a day. Right? But what is the potential hypothesis that I have now? If I just want to give you a recommendation about the number of calories a day, then here is the number of calories you can eat a day, from 0 to, say, 5,000, maybe. And we know in advance that how does my recommendation is going to look like. You can, yes. What do you say? No, just my recommendation. I want to tell you a recommendation. You should eat so many calories a day. But I'm asking, what is the hypothesis class? What are the potential answers that you can expect? You see what I'm asking? Yes.
Range.
Well, a range. So the hypothesis class is actually, all I care about is ranges. I know that my recommendation that I'm looking for is telling you it should be something between this number and this number. I'm looking for a range. And the class of all ranges has VC dimension, we know how much, just 2. It's not, because I'm not going to give you a recommendation that will say the number of calories that you should eat every day should be a prime number. If you eat, 1,500 calories, it's really bad. But if you eat 1,507, it's good because it's a prime number. We know in advance that what we care about is such range. So the class that we care about is a class of finite VC dimension, to start with. We just want to evaluate which range will do the best prediction. No range will be perfect. With every range that I'll give you, there will be people that eat this number of calories and are sick, and there will be people that eat outside this range and are very healthy. Nothing, but I want to find the range that optimizes the mistake, that minimizes the mistake. I just classify people to healthy, not healthy, and I want to give you a recommendation, which is the range. So initially, all I cared about, I didn't care about trying to predict just based on the number of calories to get a perfect prediction whether someone is healthy or sick. I cannot. I know that I cannot. All I cared about is finding the best range. So this is a situation in which there is a fixed small VC dimension class, and that's what we really want to learn. We were not here being two presumptions and say we are going to predict sick versus healthy. Okay? So sometimes finite VC classes is really what we care about. But there are also other situations in which machine learning helps. Sometimes it's not that finite classes is all we care about. I mean, if I want to predict if an email is spam or not, then you will not be happy if I tell you no. The best, if I had to give you an interval of how many words there are in the email to tell you what's the best range to detect spam or not, I'll tell you, sure, the most risky emails are those that are between 5 and 30 words. But it doesn't help you much, because that's not what you wanted. You wanted as accurate as possible prediction of spam. So in such situation, how did I call it? The argument 1. But OK, so however, there are situations in which our goal is to minimize our prediction error regardless of any class H. in such a case, picking an h is a liability. It costs us something. We suddenly restrict our attention to some hypothesis class, but maybe nothing in this hypothesis class is good enough for us. Right? So for some situation, what we will do now, we will show how we can extend learning, and that's what's really being done in practice. Learning is extended beyond classes of finite VC dimension. So the next step is extending learning beyond finite VC classes. Okay, so now, I worked very hard to show you that the VC dimension tells you if it's learnable or not. And now I'm telling you, now let's learn things that are not learnable. And this looks like, there's a bound to how much I can convince you, right? But so the trick is that we are going to change our success criteria. So we say if we want to learn, okay, so let me, before I give you the idea, let me give you an example. So assume that I want to learn for simplicity, let's do things just over the real line. So I have only one parameter. But I want to minimize the error. So I'm trying to think if I can give you an example of a phenomena that is only one parameter, and I don't know that I'm looking for intervals or initial segment. I really want to minimize the area, the error. I don't know. But this is just for simplicity, it's one parameter. But it could be emails and spam. Or it could be patients and we're trying to predict whether they're going to have a heart attack in the next year or not. So it's very important to me to have an accurate prediction, right? And so it's not one. So I have a space. I have a space, and I know. So my space is going to be the heart rate of the patient, and the blood pressure of the patient, and the temperature of the patient, and all kind of tests that I do to the patient. So it's a multi-dimensional space. And what did we offer before with the classes of finite VC dimension? We said try a linear predictor, right? So I have my patient. I have all kinds of variables that I measure for the patient. I'm trying to predict the risk of the patient, whether they're going to have a heart attack or not, by sigma wi xi, where xi is the result of the ICE test that I did on my patient. So x1 could be the heart rate, x2 could be the blood pressure, and so on, right? So I'm trying to predict by the sign of this. This is a class of finite VC dimension. If I did on my patients 20 measurements, the dimension will only be 20. But it's not good enough. I want a reliable predictor. If I am in an emergency room and a doctor and I want to know whether I should send the patient home or hospitalize him, it's not good enough for me to tell, 10%, 20% of my patients die, but what could I do? That's the best a linear predictor can do. It will not be very convincing, right? So I do believe that some function over what I'm measuring in the patient can give me a good prediction. But I don't know which function it is. Nobody guarantees that it's going to be a linear function. So I'm considering a situation in which the variables that we measure do have a lot of information. The question is what functions, what class will be good. So I can say, you see, if linear functions are not enough, maybe I should use quadratic functions. Maybe I should use functions, if I look at it as one dimension, just instead of saying y equals ax plus b, maybe I will allow y equals ax squared plus bx plus c. Now I have more functions that I can consider. Or maybe I can consider polynomials of higher and higher dimension. Note that these are examples over one variable. If I have many variables, polynomials of degree 2 over many variables. They allow me products of the variables. They allow me to take squares of the variables. And they allow me to have the variables on their own. Still, you can ask, does this capture everything? So I'll tell you, OK, so let's also consider polynomials of the 3rd degree and polynomials of the 4th degree. Does this capture anything? We know that the union of all polynomials can approximate every continuous function. So if we assume that what we care about is a continuous function, it's not that if your heartbeat is 60, you are healthy. If it's 61, you're going to die tomorrow. Things change smoothly. It's a continuous function. Then if I allow myself the set of all polynomials, then I will be able to approximate any function. Then I'll really have a guarantee that if I got the relevant variables, I can do a good job. But what do you think is the VC dimension of the set of all polynomials? So this is for the assignment 2. The VC dimension of the set of all polynomials is infinite. Otherwise, you would have been using it already, right? So somehow we want to extend beyond classes of finite VC dimension to classes of infinite VC dimensions. It will give us more flexibility, like a class of all polynomials over my variables. And what kind of guarantee can we still give if we lost the finite VC dimension? So now we get into this next step, next chapter in the book, and it is called non-uniform learnability. And non-uniform learnability comes to capture a situation like this when I want to learn a class which is too big to be of finite VC dimension, like the class of all possible polynomials, without bounding the degree. And the trick is that we have to remember what was exactly our success criteria. So success criteria, we say that, so just recall. Our definition of agnostic pack learnability. We say that a class is learnable by a class is agnostic pack learnable with if there exists a function m h of epsilon delta such that what do we get? Such that for every probability distribution over the data, and now I can write it like this. Every epsilon and delta, if my sample size is greater than m h epsilon delta, then with high probability, greater than 1 minus delta, for every h in H, my algorithm, the arrow with respect to the probability of, this is the sample size, the arrow of my algorithm with respect to this sample is at most the arrow with respect to P of H plus epsilon. So note that I did here a small change from the definition that we had before. The small change is before we said that you are agnostic learnable if the error of your algorithm is at most LP of A of S. We said is at most the optimum, the LP of the optimum h in h, or the minimum over h in h of the arrow of h plus epsilon. So that was, let me just erase the irrelevant part. That was the way we defined agnostic learnability before, but this is equivalent. Saying that you are not doing worse than the best in the class is the same as saying that for every member in the class, you are doing as well as this member in the class. So I'm just repeating the definition with a slightly different way of phrasing it. And now, how can we introduce more flexibility? Now, the way I'm going to introduce more flexibility, so here what we said is with so many samples, our algorithm can compete with every member of the class. But now what I'm going to relax is I'm going to say, if you are going to compete with a very complicated, very sophisticated H in the class, I will allow you to train more. So assume that I want to give you a guarantee. If we go back to my example of a guarantee for investing in the stock market. So I want to tell you, if you give your money to me, I'll invest it for you, and I guarantee that I'm going to give you as much profit as any agent in this big company. It's a nice guarantee. Now I'm saying something different. You know, look at those agents. If you pay me a little bit, I guarantee that I'll beat the weak guy there. If you pay me more, I can give you a guarantee that I'll beat a bigger guy there. And if you'll tell me a lot, I can guarantee that I'll even beat a big expert there. And that's what we are going to do. Because here, what we required is that the sample size that we needed would be the same to beat every H in H. Now, in non-uniform learnability, we will say, OK, we will stratify the H's and say, as the H's become more complex, I'm going to require more samples. And that will allow me to handle classes of infinite VC dimension. And that's why I call it non-uniform learnability, because the uniformity was I need the same sample size to handle the competition with every H in H. Now I'm going to stratify there the classes H, the members of H, and say, the higher they are in the hierarchy, I will need more examples. So we come up with a new definition, which looks very much like the old definition, like this definition. So we say that a class, so we have a definition. A class H is non-uniformly learnable, and this is agnostic Pak non-uniformly learnable if there exists a function m of epsilon delta h. This function will tell me if I want to beat the expert h, this is how many examples I need. And for a different expert, I may need more examples. There is a function m of epsilon delta h such that, and now everything will repeat, such that for every data generating distribution P and every epsilon and delta and every h in H, and there exists a function, and also there exists an algorithm, a learning algorithm A. If m is greater than m of epsilon delta h, then with probability above 1 minus delta, the error with respect to P of, right, and S is drawn into from P to the M, my error of my algorithm will be at most the error of this H plus epsilon. So you see, it's the same guarantee that we had here. Everything is exactly the same. The only change is that allow my sample size to not only depend on epsilon and delta, but also depend on H. You tell me who do you want to compete with, and I'll tell you how many samples I need to compete with that guy. You kind of arrange the members of this big class H into layers. And every layer we may need a different number of examples. And in fact, this is what's being done in practice, in learning. In practice, in learning, we consider classes of infinite VC dimension that really allow us to cover practically all possibilities. But we pay more as we're trying to compete with a more complex hypothesis. There is a notion of the complexity of the hypothesis, which comes into the game here. How the sample size depends on this H. Yes? It's LP. That's yeah. So let me tell you what is what are we going to show, and why is it? So the theorem that we are going to show is that a class H is non-uniformly learnable if and only if there are classes Hn, n in n, each having a finite VC dimension, such that my H is the union over n goes from 1 to infinity of those Hns. So now I can learn not just classes of finite VC dimension, but classes that are unions of classes of VC dimension. So the example that we saw, if H1 is linear function, H2 is quadratic function, H3 is functions of degree 3, HD is functions of polynomials of degree d. The class of all polynomials has an infinite VC dimension, but it's the union of the classes of polynomials of degree d. Each fixed d, the class of polynomials of degree d, has finite VC dimension. So I can learn in this way the class of all polynomials, because it's a union of classes, each of which has only finite VC dimension. So let me give you another example that, the polynomials is a little bit difficult to analyze, but let us consider a very simple example that really this gives me an extra power. So here is an example of such a class. So let x be the real numbers, or any x, and for each k, let hk be the set of all functions. H goes from R to 0, 1, the set of all such functions, such that h of x equals 1 for at most k many x's. So these are the functions that allow you to pick k many points, give them value 1, and all the other points should be 0. Right? So h1, we've already seen it. What is the class h1? We've already discussed this class. What was h1? Yes?
Single point.
The class of all singletons. The class of singletons. Okay, now I ran out of time, so I leave it to you. So prove that the VC dimension of H of the union of all the HKs, k goes from 1 to infinity, is infinite, and for every k, the VC dimension of HK is only k. But we'll do it in the assignment. So it really gives me extra power to learn things that I could not have learned before. OK, so enjoy your reading week, and we will meet again in 12 days.